wait to
Okay.
school version.
Do you think I could take this off?
Okay.
Did you not? Or no, keep. Nothing else.
First, hey, alright, here's what I'm gonna cover today. I got 3 problems I'm gonna go through. Then I'm gonna let you have a ton of time today where you can actually work on your assignment. We do have a new assignment. It's gonna be due on Tuesday next week. That is the day we're back. We don't have school on Monday. So I strongly recommend that you take your books home if you don't finish today in class. You should have plenty of time to actually work on it. Okay. Let's walk through this today just to make sure that you understand how to get these formulas. Okay. All right. The first one we did one of these I think 2 days ago, not yesterday but the day before, where it asks to find the formula, to find the equation that's exponential that represents this. It can be finding that percent of growth, but it can be in 2 different forms. I want the one without the letter E, the continuous formula. I want the one that just has the A. So it has A for the amount, A0 for the initial amount, E, or sorry, not E, but R to the T. So RT there. That's the formula that I want for this particular problem. The reason being is that we're going to find that growth rate. Now, obviously the R will be 1 point something, because one of the questions I had yesterday that Hoover that you brought up was, how do you know if it's 1 point something or if it's 0 point something? Like, where does that come from? Do you agree that from year 1 to year 3, this number grew?
Yeah.
So it went up, right? It went from 10.6 up to 18.9. So my R in this particular case is going to be 1 point something, right? It's growing by a certain percent. That's what we're going to be looking at. Now, to figure out what that R is, to figure out what that growth rate is, here's what you do. You divide these numbers. You take the later date, which is year 3. We put that on the top. We're going to divide by year 1's number. This will give me that percent of growth. But it's not the perfect percent. It's going to be off a little bit. Because I don't know what my initial amount of people was. This is the amount of people or substance after year 3 or after year 1. So the idea is over here is we put the formula for all the numbers we do know. Like for instance, I know after year 3, the amount grew to 18.9. After year 1, I knew that the amount grew to 10.6. So that's the idea. So I'm plugging the numbers I do know. I don't know the R, and I don't know what my initial amount of people was. Okay? I don't know what times 0 was, T of 0. My initial group. Now at this point, what happens here? If you divide these, this will give me that percent. The A0s cancel out. So then I'm left with R to the 2nd power, because you'd actually subtract. That's cancellation method according to Algebra 2. You can simplify variables, right? Over here, you divide these. This is where a calculator comes in handy. 18.9 divided by 10.6.
1.78.
1.78.
Yeah. Wow. Well.
Is there any more decimals after, or is it just a nice 1.78?
1.7830188868.
Why did you do the 18 over the 10?
1.78.
It's always the later time over the
8868.
former time. So the reason why is that if the later time is bigger, this number will be kind of a larger number. That's what I want. If it was getting smaller, then yeah, your later date will be a smaller number, so it'll be like a decimal. It's shrinking by a certain percent. Yeah, good question. It is a good question. Now, next thing. We have R squared equals to 1.78301 blah, 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 blah. We need to take the square root, because I want to get the R by itself. So, to get R by itself, we take the square root of this 1.78301 number, blah, blah, blah. Try to use as many decimal places as you can. So you have to get used to those square root buttons. And what do we get?
1.3352979.
529.
7296.
Okay. Am I close?
Yep.
Okay. So, what this thing is growing by, if I'm looking at this correctly, my R is growing by 33%. 33.5 something percent. It's 100% of the population plus extra. And so now I figured out what my R is. So my actual formula that's being represented here is this. This is the 1.33529 blah, 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 all to the T. This is the formula that's representing. I could actually figure out what my initial population could be, because I can go back and figure that out, because now I know what year 1 would give me. Year 1 would give me, I put a 1 up here, I put the 10.6, I can figure out what A0 is, because you can divide this number over. So, I can figure out all the numbers I need now. I can get the formula with everything plugged in. But does everyone understand why I took that number and I put it over there for the R?
Is this what our problems are?
There's 2 of these or 3 of these you're gonna have to do.
What is the rest?
So the rest are the ones where you look at a graph and see, okay, is this increasing? Is it decreasing? Is it concave up? Is it concave down? That's the next part that we're gonna talk about. And then the other ones are, is it linear or is it exponential growth? We're gonna look at those. And it's based on this stuff.
I said.
Okay, all right, are we good so far? I'm not done yet.
I can see it.
Oh.
Okay, we're not done. We're not done, because remember, I still want to find a of 0. So, because I want to get the entire formula with everything plugged in. So, doing this, so I have my t is 1. Now this is just my example so I can figure it out. I'm going to plug in my t of 1. And I knew that my initial population grew to 10.6 that first year. So now I can solve for a of 0, my initial amount of people. Because I can 1.33529 to the first power, it's just that. And I can divide this number over, and now I have my R number, or my a of 0 number. So if I divide that over, what is a of 0?
0.
Now it's going to be
1.
10, 6,
7.938.
8938.
Oh, no, I thought you were talking about what's on the end.
938.
938, okay. Sorry.
938
There's no 8 right
307
after.
098.
Thanks. Yeah, there's probably more decimals. Yeah. Okay, there's my initial amount. So I have every number I need. I have my R, I have my initial amount, I have everything I need from that problem. That's what the first, there's a few problems, I think 3 of those that you have. They just give you this and say, hey, find your rate, find the initial amount, find all the weird numbers you need from that data. Okay, are we good with that one?
Sure.
Okay, now there's a couple problems I'm not going to go over from yesterday that we talked about where it was like, how do you know if this is increasing? How do you know if it's decreasing? It's basically just looking at the formula. Like I can look at this formula and say it's increasing. It's increasing by 33%. I know it's going up because of that number. Or if you had the E number, the number in that K spot or the R spot in the E, if it's positive, it's increasing. If it's negative, it's decreasing. Those are like, you have 3 of those. Like those are easy. That's just like quick, yeah, it's increasing. Are we good with these so far? Now here's my question to you. Do you want another one of those or are we comfortable?
We're comfortable.
Another one.
I'm
pretty
comfortable.
Pretty good.
No, candy.
Okay. No, no.
I would like to move that we are done with this problem.
No pomegranates.
Okay, all right, here we go.
Pomegranates.
All right. Let's go with this. All right,
Motion.
we'll do one more. I'm gonna just do this kind of fairly quickly to make sure we get the idea. Okay, on this particular problem, this is my next example. Do we agree that it's decreasing?
Yes.
Yeah.
Yeah.
It's going from year 4 to year 5. We're decreasing. We're going from 7 of some substance down to 5. So it is getting smaller. Now, the idea is that you still take the later time divided by the former time. So like the days that are later, like the years that are later, that goes on the top. The years that are earlier go on the bottom. This is a to the 0, r to the this would be 5. This would be a to the 0, r to the 4. So what happens here? The a's would cancel out. This would be r to the first power, because 5 over 4 would simplify. And when you divide 5 divided by 7, we get some weird decimal 0.714.
714.
Okay, now, do we need to take a square root or a cube root or any weird stuff? No, because I have an r to the first, that's my r. It is definitely decreasing. In fact, I'm decreasing by like 39% almost, or 29%, sorry, 29. Because 29 will take me back to 100. So I'm actually decreasing by quite a bit here on this decay rate. Then what I can do is, now that I know my r, I can go back and plug it back in. The 0.714 blah 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 to the t. Okay, do we understand how I would take that number and plug it right back in R and keep going? Now, obviously to find a of 0, I'm going to have to put my amount. Maybe I can put the 7 here and put the 4 up here and then go ahead and solve. But that means I have to put this number to the 4th power and divide by it, and that will give me my a number.
Does it matter which one you use?
No, it doesn't. It will always give you the same, because if it's true exponential, it works no matter what data point you pick. Yeah. All right, questions at all about that? Okay, let's go to the next one. These are the ones, the next problem I want to pick is whether you know it's increasing or decreasing, or if it's concave up or concave down, that type of thing. So that's what I want to look at. All right, these are ones we talked about a couple days ago, like 2 days ago, but we never really got back to yesterday. Yesterday was mostly focused on the math like we're doing here. Where you figure out, you know, E and radicals and whatnot. Okay. Okay, here we go. Let's put some data points in here. Okay. All right. Let me get some letters here. A, B, C, D, D. Okay. At this point, let's start with increasing and decreasing. So this is a function. The function itself is this line that's in red. I tried to put arrows. So it's some type of a curve. It's not strictly exponential, but it is growing at different rates. Correct? It's like going up and down. So it is a curve. So what they're trying to get you used to seeing is like whether you are increasing over a certain time, if you're decreasing over a certain time, and then the next thing we'll talk about is if it's concave up or down. So from this moment, from here, from this direction up to B, what is the function doing as I go from left to right? Is it going up or is it going down?
Up.
It's up. So this part right here is increasing. It's increasing until it gets to B. After B, it starts to decrease a little bit in terms of function, correct? Like in terms of values.
Yes, sir.
Okay, then eventually when it gets to letter D, so this is now decreasing, right? So then when it gets to letter D, it's going back up and it's going to increase again.
Yes, sir.
And it will increase pretty much the rest of the time on the graph because the arrow tells me that. Now, the weird part is, at certain moments on this graph, there is concave up and concave down for concavity. Concavity is, the idea is when it switches from increasing to decreasing in terms of numbers, like it starts to slow down and it starts to change directions. It's not the perfect turning moment, it's not like B and B. It actually starts to turn before that. So like for instance, this part right here, up until letter C, up until this point, this is concave down. Up until letter C. Because after C, do you notice that it's starting to bow upwards, like a bowl? So this would be concave up from here, from letter C and on. So it's like, is the bowl dumping out, that's concave down, or is it holding water, that's concave up? Now, why that's important? Because this is the actual inflection point of turning. That's when it actually made some type of change. Something happened at that moment, it's almost a critical point. Those are things we're going to discuss at some point. It's like a major topic. Now, why they bring it up is because exponential functions are one of the first functions we look at where there's curves. So they want you to get used to the vocab again. I believe we have talked about concave up and down and increasing and decreasing in pre-calc, correct? If you remember that?
Sure.
It was like the first chapter or two back in pre-calc, but it's one of those things they just want you to review. Nothing crazy in depth. They're literally just going to ask, where is this thing increasing? Well, it's increasing from A to B. Where is it decreasing? Maybe from B to C. Is it increasing anywhere else? Well, it's increasing from D to E again. Is it concave up anywhere? Yeah, from like C to E, it's concave up. So they're going to ask for different letters and getting used to graphs. They want you to be able to interpret when you just look at it. Okay, questions at all about concave up and down?
Nope.
Perfect. The last thing I want you to look at is if you had a table, this is the last type of problem. I'm just going to give you a rough example here. -1, 0, 1, 2, 3. Okay. So, let me give you an example. Okay, let's see, can I go to a table? Okay, from All right, so on this one here, I'm gonna put data point as -2, this is a 1, this is a 4, this is a 7, this is a 10. On this one, this is 0.5, 1, 2, 4, and 8.
This is the zero.
Okay. Okay, so I gave you some different data for this thing. So what they're gonna have you do is look at the table. It's kind of like that first problem I did for you earlier. And what they want to know, is this linear or is this some type of an exponential curve? Because obviously, I can tell if it's linear because what's true about lines?
Straight.
They're straight, so that means their slope would have to be the same, correct? It would be straight, right? They're not going to change direction. So if I were to check slope at any point, the slope would change if it was a curve. Like it would certainly start to ramp up and be more steep, so the slope would change. So that's what they're looking at. Is it actually exponential or is it an actual line? And they're going to have you compare two different functions. This is function number 1, that's function number 2. These just happen to be the x values that they're using for each problem. So to check whether it's a line or not, I'm going to figure out the slope from here to here, the slope from here to here, and what should happen, and you can do it any 2 pair, I'm just picking 2 numbers at a time. No matter what you pick, if it is an actual line, the slope should be the same no matter which one you pick, if that makes any sense to you. If it's a curve, the slope will probably change at some point between these. So then you know it's a curve and not an actual linear function. So now, to talk about slope, because we did talk about slope, what, 2 days ago when we were discussing it, I think? To talk about slope, here's what you do. You subtract the y numbers. This is the generic formula of it. And then you subtract the x numbers on the bottom. So, I don't really care how you pick this. I'm going to call this y1 and y2. I'm going to subtract those. This is x2 and this is x1. I'll find the slope between those. Because these are y numbers. These are the x numbers. So, I'm going to go, so the first one I'm going 1 minus a -2. And then I'm going to go 0 minus -1. So I'm going to y2 minus the y1, x2 minus x1. This turns out to be a 3 over 1. So there's the slope. Going later, let's go down here. I'm going to go 10 minus 7, 3 minus 2. I'm checking that slope. This turns out to be 3 over 1. So what can you tell me about this graph right here? Just by looking at these 2 data sets. It's probably linear. If I check the others, they're all 3s. It's a line. I made it a line. But you'd have to check multiple data points. On the other one, no matter where you pick, say I pick these 2 and these 2, I don't think they're going to be the same. So let's walk through this. So 1 minus 0.5, I'm subtracting 0 minus -1. So there's that data point. I'm checking this one right now. And this one down here, this is 4 minus 2, and that is 2 minus 1. So this ends up being a 1, this ends up being a 2, so there's that slope. This slope up here, this turns out to be 0.5 over 1. So do you see that the slopes are different? It's not a line, it's a curve. I can automatically tell it's a curve. The slope has changed. So they want you to understand, like, the questions would be, tell me more about function number 1, function f. Is it a curve, is it a line? How do you know? That's how you do it. You just shows them. That's the question. They want you to interpret data.
We should do that over 4 onto that.
Yeah, so you can just kind of pick and kind of choose.
What if I went 0.5 and 8? Can I do that?
I mean, just because if it was a true line, the slope would be the same.
Alright.
So it's just one of those things, I want you to be able to look at data just really quickly, like very generically, and see kind of what type of data you're looking at. All right, homework's on the board, page 17, 2 through 4, 6, 7, 9, 10, 13 through 17, 19, 22, 24, 31 through 34. It's straightforward. If you have questions, I'm going to be making the answer key. Homework is due on Tuesday. The rest of the time is yours. Make sure you have a calculator, you'll need it. If you need to go grab a book, I'll give you a pass here in a second.